Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Today we are welcoming Byung-Soo Choi to our group. And he got his PhD in South Korea. He's currently a postdoc at Duke University and has been working with the Quantum Computer Science IARPA program on a team at Duke University. His interests are in the areas of quantum computer architecture and previously in microprocessor architecture. So Byung-Soo is going to today present work on quantum computer system components for quantum augmented cloud systems. So please welcome Byung-Soo. Thank you.
Thanks so much. It is my great pleasure to be here. And this is the first time for visiting Seattle. It's a very nice place. And I'm very proud of the Microsoft because Bill Gates is one of the respected persons in the IT societies. So this is very good. And this is very honor for me. Okay, today I'd like to discuss, or not discuss, I'd like to talk about my previous work and my current work related to quantum applications and quantum systems. So ultimately, I want to, if I work in this world more than 20 years for the rest of my life, then I want to look at some quantum system in the cloud systems. And then I'll be very happy if everybody can use the quantum computers. So let me start. So my talk will consist of three parts. One is my broad view of the quantum cloud systems. And second one is my previous work. And the last one is my current work and my plan. So when I started this work, when I started quantum research, from the time I consider how can I design the quantum cloud systems from the device level to the algorithm levels. So from this slide actually made it around 5 years ago. From the time I revised again and again based on my knowledge about quantum systems. So please tell me if I have any incorrect or if I have invalidators. Please just tell me. So I consider the quantum computer system consists of these hierarchies. So at the low level, we can make a quantum device, like a qubit gate operations based on the physical device, like ion trap, optical ray, superconductor, and NMR, or solid state, or whatever. So although we have a quantum device like this one, but if we don't have any quantum computation model, then we cannot do that. We cannot make a quantum system. So we usually have three. These are my classifications. So we have three models, like a circuit-based model and measurement-based model, and now we have another one, like anion-based models. So circuit-based model is very similar to conventional circuit-based, conventional classical computer models. So we just make a circuit and we just run the circuit. The next one is measurement-based models. So if we prepare a large number of APR pairs, and we can do measurement among them, then we can do the computations. So we call this as measurement-based model. Now another ones, recently, based on the anions, we can make a quantum computation models. So these three things, I think these three things are major computation model in the quantum computer, but there's another one like Arithmetic. And also maybe we can propose another one based on cellular automata. So I believe that there are so many models, but typically we have three models, like circuit-based model, measurement-based model, and anion models. So now we have a device, and we have a computation models, but this is not enough because this quantum device is very sensitive to the errors. So we have to apply error correction code or fault tolerance schemes. So we have to use some fault tolerance primitives like a concatenation code or topological code or surface code. So this layer technically for the error correction part and fault tolerance part. So these three level device, model, and error corrections can make one scalable and fault tolerant computation models. But that's not enough to make a quantum computers because we still need some components like adder or Fourier transform or multiplier. These kind of things, in conventional terminology, we call these database elements. So we have to make those kind of things. And also we have to make memory systems or CPU or bus systems. Or maybe we have to add another one like a communication components. So based on these, we can make distributed or multi-node systems. Up to now, I do not believe that we can make one holistic, one big systems, one big quantum systems. We have to make an internet communication system between the nodes. I think that's the practical way how to make a big quantum computer system right now. So we have to consider this distributed way. So up to this level, we can make one working quantum computer system, but that's not enough for us. Right? So we have to build up, we have to make another layers, like system software primitives, like a compiler, scheduler, or optimizer, and other things. So I call this one quantum CAD systems. So these levels, this hierarchy of the levels makes quantum computer systems. Or we can make a connection between the computer. So we can put some components here for the communication part. So based on these hierarchy and the structures, we can make a quantum systems. Now, the next one is applications. So I'm considering this architecture. This is a cloud computing systems. So currently, right now, in the classical domain, they also do a lot of work on the cloud computing systems. But at the same time, we have to consider how to use that, how to use a quantum system for the cloud systems. So I made this level of components. The one is the lower layer is application primitives, like high performance computing algorithms. And second one is high secure applications. And the last one is high-speed communication primitives. So these kind of primitives can be used for making applications. In the conventional cloud systems, they call this as an application as a service. So based on these primitives, we can build up some applications like computational science, engineering applications, or healthcare, or transportation, and whatever. But for that, we have to have one middle layers, like application framework layers. So this framework have to map these application primitives to the applications. So in this case, we have to combine the classical cloud systems and the quantum cloud systems. And the last one is just a device or the user interfaces. Like me, individual cases, and like a company like Microsoft or other companies, the business sectors, and another one is the national sectors. Usually, we have to use quantum system. Firstly, we have to consider the national application first, probably like a national security or national energy partners. But sometimes later, we will use this one for the business sectors, like a bank or Microsoft or Google or Apple systems. But finally, like me, I also want to use quantum systems through my telephone. Okay, so this is my big picture of the quantum augmented cloud systems. So this is the system level, this is cloud system level, and this is the end user or the terminal or the embedded systems. So as you can see, this is not a big job. This is not a small job. This is very big jobs. We have to consider vertical integrations of all areas, from the device level to the application layers. So the impact of this device, the property of this physical device will affect whole things. Also, the application will affect the device as well. Yes?
If you spread quantum components distributively,
okay,
then new security problems arise.
Yes, that's true. That's true.
They're going to address them.
Somebody have to do that. Maybe I cannot do that, but somebody have to do that. So we also recognize that kind of problems. For example, if you have to make a global quantum network systems, how can you manage the security from the attack from like North Korea or from other countries? So those security issue is very important. Also, in the cloud system, conventional cloud system, the most big problem is security. So we have to consider the same things in the quantum case as well. But luckily, we have some high secure systems like QKD systems. So maybe we can support much more higher security compared to classical systems. So
But I'm surprised that I don't see quantum information. You know, quantum has something contribute to security, to the secure way to exchange bits, quantum more secure than anything else.
yeah,
I think what's missing from Yuri's comment is, if I may rephrase, is there's no quantum information backbone here in the
Right.
cloud, where you can take advantage of the fact that you can send entangled states,
Yeah.
you can send
Yeah.
superpositions, and you can send cryptographically secure messaging throughout the data center, even across data centers.
yeah.
And that also needs to be on your bus, besides conventional distributed processing, quantum distributed processing,
Yeah.
as part of the hybrid. That's
Yeah.
all.
Yeah. So this area, have to consider that ones.
Mhm.
So like a network system as well.
Exactly.
Yeah. Okay. So this is my dream, to make these whole systems in my life. So related to this, before come here, I have worked on some part, especially application part and the system part. Related to application part, I do some work like cryptanalysis and machine learning part. And the system part, I do some work on the architecture part and arithmetic and code parts. So today I try to tell you about this previous work and also my future work. So applications, this is my previous work. When I joined this world by myself, and myself also want to know that whether this is really useful. This is really helpful for information processing. So for that, I do some work to analyze the quantum search algorithms. So at the time, I worked on the partial search algorithm, partial search problems. Partial search defined as searching problems, but not to find the target element, but to find the block address of the target element. So this is a little bit partial problem. This is a little bit weak problems compared to original group of search problems. But in this case, because we put some relax on the problems, so we have to ask some high success probability compared to group of algorithms, group of problems. So with other papers, we found that one way how to do that. But the idea is very simple. We can define the three bases. One is target state, and the second one is other state in the target block, and the other state, the other basis for the other state in the non-target blocks. So based on these three bases, we can find some phase conditions to achieve the success. Certain success probability is very high. The next one is we try to extend this problem for the more general cases. Like a group algorithms, we also consider the multiple target cases, multiple target block cases. This is trivial. So we found some way how to do that. I don't want to tell all details, but I just want to say that what I did. After that, I tried to move to find some real or some more practical problems. But still, it is a little bit artificial. We are given one Boolean functions, and we are also given two weights. But we don't know which weight is the real weight for the given function, given Boolean functions. Okay? So the problem is we have to decide that which one is correct one. So for that we propose one algorithms. But the idea is also simple. From step 1 to k-2 steps, we apply the conventional group algorithms. But from k-1 to k steps, we apply some modified group operators based on some conditions. So this is algorithms. So as you can see, from one step to k minus 2 steps, we apply the conventional group operators. But for the k minus 1 step and k steps, we apply slightly different group operator based on the phase conditions, theta 1 and theta 2. These are the phase conditions. But the idea is like this one. So because we are given two weights for the one Boolean functions, we can put these two weights at the initial state on the block spheres, like that way. So in this case, we assume another condition. The Boolean function is symmetric. So the summation of two weights, weight 1 and weight 2, should be 1. So that their location in the block sphere should be symmetric. Symmetric means if this one is going down, then this one should be going high. So like over this xy plane, this should be symmetric, like that way. So this is a trajectory on the block sphere for the last two steps. How can you do that? So in the algorithms, this is k minus 1 steps group operator. This is k steps operators. As you can see, we apply the conventional inversion for the target state, like pi angles. But the next inversion have to be changed based on these theta angles. So group operator, as you know, group operator consists of two inversions: inversion over the solution state and the inversion over the initial state. So we just need to change the angle for the inversion over the initial state. So this trajectory shows that. So if this is some state after k minus 2 steps, we apply the inversion of the solution state so that this state have to be here. But next inversion over the initial state, this next inversion have to be changed based on angle theta. In the previous slide, these values. Okay, so we found that the angle based on these conditions. Okay, in the trajectory, based on these theta angles, we have to rotate this state into somewhere here. Okay. Yes.
What is the weight? How do we assign weights to Boolean functions?
Weight is defined as a ratio of the number of solutions over the number of input space. If there's only one solution means just some input shows that output there's one.
Satisfying assignment.
Yeah. Number of satisfying.
So the fraction of satisfying assignment.
Yeah, that's correct.
So you don't know ahead of time. The weights are not known ahead of time.
We are given just two weights, but we don't know which one is correct one. That's a promise. We are given the one Boolean functions, and we are given two weights.
Promise problem.
Yeah, promise problems.
Okay.
But we don't know which one is the correct one. So this algorithm is for that cases.
Okay.
So during this work, we found that one way how to do that, how to distinguish this, the right one. And the next one is the generalizations. In the previous case, we assumed that the weight of these two is symmetric. That means the summation of these two weights is 1. But now we make some relaxations. So in this case, we do not have such conditions. So the summation of two weights can be from 0 to 2. Okay? This is asymmetric cases. But the idea is tricky, and the idea is very simple. So we just make a larger input space by adding some qubit, so that we can reduce this problem to the symmetric cases. Okay. So this is a way. So we can make another functions based on the initial functions. For the initial input space from 0 to n, we use the same functions. But from n to 2n, we use similar functions. But actually, this is the same functions. But from 2n to 2n plus l, we assume that the output should be 1. And for the other input space, from 2n plus l to 4n, we assume that the output is 0. So this f prime function is derived from the f function f, but the weight is different. So because of this distribution of the solution space, we can make W1 prime and W2 prime, and their summation can be 1. And the condition for L is derived like that way. So this is very trivial, and this is very simple ideas. So the one thing I want to emphasize that the necessary qubit, usually 2 qubit is enough. Even though problem seems to be very general compared to previous cases, but 2 qubit is sufficient. And next extension is to the case for multiple weights. In this case, we have m weights. Then we want to decide which one is correct one. So the idea is to apply the sequential or repetition of applying the asymmetric case algorithms, like that one. So if we are given these m number of weights from W1 to Wm, and we want to know which one is correct one. So we choose two candidates from the S. The one is the minimum and the one is the maximum. And we apply the asymmetric weight decision algorithms, the previous one.
But now it's not promised that it will be one of them. You need the promise that one of them is correct.
Yeah.
But it may be neither minimum nor maximum is correct.
That's right. So in this case, we have a promise. One of them is right weight. But in this case, we just choose that. So sometimes we choose W1 or Wm, but unfortunately, W1 and Wm is not the correct one. Then this algorithm shows that or gives us some candidate likelihood weights, not the correct one. Okay. Based on that, we can choose that. But even in that case, we can say that not chosen or not selected weight is not a candidate. So we can destroy that. We can ignore that. Okay. So this is knockout systems. So every repetition we just knock out one by one. But if sometime later, if one of them is the right one, correct one, then that weight can be chosen, and that weight can be survived for the whole remaining iterations. So we can choose that right one. So this is one way how to do that. So finally, we did not consider any more generalization of this problem. So our last job is to prove that whether this is optimal or not. So we tried that. We tried to prove that whether this is optimal or not. So for that, we apply the quantum query complexity methods, quantum query analysis method. So we exploit the unbiased quantum adversary method. So he proposed one way how to do that. So if he can find some relation R, and we can find some input space X and Y, and if he can find these kind of conditions, then we know that there are at least this number of queries are required to do the computations. So we apply the same idea for our case.
What do you query? Where is the oracle?
Sorry?
You count queries. Queries to what?
Query means oracle, number of.
And what does the oracle do?
Oracle is F. It's the
Yeah.
function.
Yeah. In quantum algorithms, usually.
Oh, F is a function.
Yeah, F can be implemented by oracles.
Fine.
So, this is just a query, not circuit complexities. So how many queries, how many oracle functions required for doing these algorithms? So based on this information, we can infer whether this algorithm is optimal or not. So we just apply the same ideas in our case. So for our problem, we found that these values from M to L prime, and we just applied that same algorithms. So we can prove that our algorithm is optimal. So this whole thing is, yeah.
The result.
Okay.
So theorem 7 is symmetric.
Yeah.
Requires k queries. Where k is what?
K is a number of steps, and the number of steps means number of group operators. how many group operators have to be used for doing these algorithms.
So coming back, is your algorithm optimal or not? You didn't return to it.
Sorry, say again, please.
You pose a question whether your algorithm is optimal.
Yeah, I mean, our algorithm requires case steps for the problems. And based on this analysis, we found that case steps are required.
In that sense, it is.
Yeah.
Okay.
Yeah. So this one, this whole thing is actually for my understanding of the quantum computational power for some algorithms. But luckily, this kind of problem can be used for machine learning right now. So I'm extending this idea for machine learning cases. But from now, I'm trying to explain that my previous work on the quantum system part. So to build up the quantum systems, we have to consider many things. But in that case, we cannot do anything. So I just considered some simple cases, like an adder circuit first. Based on this, I can get many insights about the depth row bound, and the scheduling, and the error analysis, and the row bound as well. So I choose the adder for my primitive for the research things. So my first question on the system part is, what is the depth row bound for the addition on the 2D architectures? The question is, this architecture is very important in these cases, because this one, 2D NTC plus swap channel means we allow just the nearest neighbor interactions between the qubit, and we allow just the 2 qubit gate operations as a maximum, and we allow the concurrent gate operations on every qubit, and we allow just the swap channels for moving the qubit between the neighbor. N means nearest neighbor, and T means 2 qubit gate operations. We allow single qubit gate operation and the 2 qubit gate operations. Okay. And C means concurrent operations. Okay. So my question is, in this architecture, 2D NTC with the swap channels, what is the depth row bound on the additions, for the additions? So for that, I exploit the graph theory approaches. In the graph theory, we know that some graph embedding issues, like these cases. This is a guess graph, and this is host graph. And our job is to map this guess graph into the host graph. Okay? Because if the host graph has some limitation, like this one, then the guess graph have to be changed. Have to be changed means some edge, like this one, have to be, the distance of this edge have to be changed, like this one. So this is one case of the graph embeddings. So this guess graph, this is a tree, and this one is a line graph. So this edge from node 1 to 5 have to be changed like this one. So in this case, there's no direct edge from node 1 to 5. If they want to communicate, they have to use node 2. So that means this interaction distance have to be increased in these graphs. Okay? So we just use this idea in our case. So we found that there's some factor like a dilation. The dilation is defined as a ratio of the diameter of the host graph and the diameter of the guess graph. Diameter is the maximum distance between any two nodes in G. That means, in this case, diameter is from node 1 to from this node to this node. Maximum distance of any two nodes. Okay. Yeah.
So what you call embedding is not really embedding.
It's just mapping, actually.
Mapping.
Yeah, mapping. Mapping is better than.
And Unger's theorem is about two embeddings, right? The next page.
Yeah, yeah.
This theorem is about two embeddings, right? Formula 2.
Yeah.
Okay.
Yeah. So this dilation value implies the increase or the overhead of the edge, the increase of the distance for the guess graph. Okay. Based on this dilation effect, we know that we can infer how much ovoid have to be added for the distance of the every edges.
How much you have to dilate the host graph in order to embed properties?
Yeah, that's correct. That's correct. So luckily, in the addition circuit, the addition, in the graph theory, addition can be implemented by the tree graph. Okay? And this 2D NTC can be represented as just a grid structure. So in graph theory terms, the problem is like this one. So we want to embed complete graph structures into 2D graph structures. Then how much dilations? So that's the key. So based on that, we found that this is a low bound of the depths. Depth, in this case, depth means from this leaf node to the top node, because addition is just from this leaf node to the top nodes. So based on this algorithm, based on this property, we can found that there is a low bound like these values. So if we are given KD NTC architecture, then the low bound is this one. So for the 2D cases, the depth low bound is square root of n. Okay, so we found that. And the next question is, then what about the depth optimal adder of the 2D architectures? So we propose one adder based on the partitioning of the input qubit, like that way. So we put the adder like this way. So the number of column is root n, and every column contains root n elements. So there's n qubit, and we map the quantum addition circuit on this architecture like that way. So this is a first phase. In the first phase, the first column have to do the conventional ripple carry additions, but the other columns they do not do that because their input carry is not defined yet. So they just do carry Lagrange operations. Okay. And the next step, because we found that the carry output for the first columns, so based on this carry output, we can propagate this carry into every columns. So every column can know that what's the input carry for each columns. And the next step is to do just ripple carry additions for the every columns. So 3 steps like that one. So this is a first phase and the circuit. So this is first column for the first phase, and this is other columns from 2 to root 2n columns. They are doing this. They are doing just the carry Lagrange operations. And this is circuit for the carry propagation between the columns. And this one is for addition from the column 2 to root 2n columns. They are doing just ripple carry additions based on the input carries. So this is one example for the 9 input cases. So as you can see, the depth is just root 2n because the time for this addition is root 2n, and this carry propagation requires root 2n times, and this addition also requires root 2n times. So depth is root 2n. So this is our one design, which is optimal, and we compare whether this is really good compared to 1D NTC architecture adders. So we analyze that whether these 2D NTC shows that better performance in terms of KQ. K and Q means number of qubit and number of gate operations. So this is a value when this 2D NTC adder shows that better performance compared to the 1D NTC adders. Because this is a simple one. So from the n is 3, this adder shows a better performance. But this one is large one, the CDKM is very good. So unless 51, this adder shows a better performance compared to our one. But larger than the 51, our adder is better than one. So now, by the way, right now, in these days, we consider KQ very important because it depends on the KQ values. We have to decide the error correction levels and the device error requirement. So nowadays, KQ factor is very important. So this is.
What was the other rows? AC?
Oh, this is AC means arbitrary. Actually, this is abstract concurrent architecture. Abstract means they do not care about the distance. So they allow any combination of the qubit operations regardless of the distance. So this is a kind of theoretical boundaries of the additions. So yeah, those kind of works are my previous work on the system part. But from now, I'm trying to tell you about my current work on the system part. So recently, the quantum computer research work is heavily focused on the research part. Because we already know how to make a photon quantum systems. But the problem is the research is too big. For example, if you want to do Shor algorithms for the 2000 bit, then we need 10 to the 20 qubit with the 10 to the 30 gate operations. But technically, this is impossible. Actually, I'm working on some experimental papers. When I say I need 10 to 20 qubit, then they say, "Oh, you are just idiot," because they say our best is to make just a 3 qubit. So there's very big gap actually. So our job right now is to reduce. We have to reduce resource overhead as much as possible. And also we have some performance metric like ADCR. This is for algorithm levels. So how many areas, how much area, and how much delay, and how much repetition of the algorithms are required for doing the algorithms. So our job is to reduce ADCR considering resource overhead. So we have to reduce the resource overhead, and also we have to reduce this ADCR. So this is my understanding of the resource, understanding of the overhead breakdown from the algorithm level to the device level. So the algorithm designers, they just make some lines, several lines. Or we can program using the C or using the F# or using the scapular languages, whatever. So this is a resource overhead in that case. Several lines or 100 lines. That's enough. But by applying the compilings, we have to decompose this source code in terms of reversible circuit so that we have to add the additional overhead. This comes from this synthesis method. But that's not all. We have to do again for the single qubit gate operations, especially like arbitrary angle rotation gates. So we have to decompose again. So this is additional overhead for these single qubit gate operations. But that's not all as well. So we have to add another layers for the error correction part and fault tolerance part. And also we have to consider architectural constraint. So this kind of things increase the resource overhead as well. But that's not all as well. So we have to do again the flattening of the sum part. So like that way, hierarchically, we have to add resource overhead step by step until to generate machine code levels, machine code. So our job is to reduce this whole overhead by optimizing every levels. But my focus on right now is to these two levels, architectural part. Okay. So my approach is to optimize some components like arithmetic part, and also improve the architectural part and then the necessary system softwares, and also try to exploit some code composition method. First one is arithmetic part. Even though we have a lot of papers, we have a lot of works on the arithmetic part, but still it is not sufficient because most of previous work focus on depth or size or gates. They do not consider usually area and delay, composite of the area delay, or they do not consider error correction parts. So right now we have to consider these factors. So maybe the immediate goal is to find some AD or KQ optimal adders on the 2D layout. But probably we just need to revise the previous designs like that way. So I'm considering right now this way. So if you can put some bus for the communication channels, then maybe we can reduce the delay for the computation part. But because this bus is not a free one, so we have to increase the resource overhead like area. But if we can put this bus very well, then we can make the smaller KQ. We can make a very good adder, which has very small KQ values. So this is one way. The next one, this is just a slide. This is just working diagrams. The next one is, I think this is much more practically important. Conventionally, we assume that after every gate operations, we have to apply error corrections, right? But if you consider just the CR or error probability of the algorithms, then maybe we don't need to do that. Maybe we just put single error corrections for one part. If the value of ADCR is very small compared to applying error corrections for every cases, then we have to choose that way. Because our main performance metric is not just for error probability, but ADCR. So we may find some best number of error corrections and their locations in the circuit, so that maybe we have to increase the area and delay, but we may decrease the error rate. So we can find some trade-off between the number of error corrections and ADCR values. So for example, we can put error correction only for this part, or only for this part, not all of them. But we don't know yet how many error corrections are required and what is the location for them. And also we can consider other arithmetic components like a multiplier, or even more, we can make another arithmetic component like a 40-point representation arithmetic or a codec. Codec is very useful for the classical high-performance computing devices. So we can make quantum codec arithmetic circuit. The next one is architectural part, and this is my main area right now. So repeatedly I say that we have to optimize the ADCR, but how can you evaluate ADCR? So technically we have to have some tool set to evaluate this A and D and CR, but this tool set also have to focus on architectural part, architectural constraint, and also error correction part. So this architectural research or architectural consideration is very important to judge that, which error corrections, what kind of parameter have to be considered. So in our teams, with our team members, we are focused on how to build up the good architectures and the necessary layout and scheduling algorithms, and how to evaluate the whole impulse. So our target architecture right now is 2D NTC architecture, but the communication channel is a little bit different. Previously, we considered swap channels, but right now we consider constant time communication channels by applying or by using simultaneous income swapping. Actually, this it is based on the Rosenbaum's papers, and also based on the measurement-based models. So we can apply the simultaneous income swapping. That means we can prepare EPR pair among any distance qubit at the single times. So we can implement constant time communication channels by using this way. So by using this one, we can do remote CNAT between any components, and we can do teleportation in a single time. So based on these architectures, our job is started. So our job is to make one architecture which exploit this kind of communication channels and to consider this kind of architecture constraint. So to make an architecture from the empty space, it is quite hard. So we check that assembly code, because this assembly code is an input to the architecture part. So this is one sample code from the another team members in our project. So they give us one assembly code, and this assembly code consists of some modules, like we call this a level 0 gates. So this is component represent one logical gate, one gate operations for the components, like just preparation of G states, 0 state actually. And this one is for measurement at the G basis. So this is primitives. And also we can define the signal operations. So these things are elementary component for building the whole algorithms. So this is a next step modules. So topology 1. Topology 1 consists of calling the low-level modules. In this case, low-level module means this level 0 gates. Okay, so this is the block diagrams of the hierarchies. So this topology 1 calls some signals several times because of this code. Like this way, we can make a hierarchy of the modules up to time levels. So this is time level. There's time level main modules. Main module consists of several sub-modules, like this one. And each sub-module calls another sub-modules. So we found that there's a hierarchy like that way. And we found that there's a modular ways. So based on this insight, we propose one way how to make architectures. So our idea is very simple. We have to make modular approaches. We have to follow the hierarchical approaches. So this is our ideas. If you can make the architecture, if you can make a schedule, and if you can make a layout for module 1, and if module B try to call this module 1, then we just map these input parameters to this module 1 by using some way. Actually, some way means shared bus. So we can lay out all modules like that way. And then if you can, and we can schedule these mappings by using some additional resources. And then we can make all input algorithms like this way. So for this architecture, we define some primitive component like a bus. So this bus implement in terms of swappings, simultaneous in terms of swappings. So this component, they can do so they can support in terms of swapping between these two neighbors. Okay. So we can implement in terms of swapping from this port to this port at the same time. So that means by using this bus, we can make some information channels from this part to this part. Also, yeah.
Previous slide.
Yeah.
So this is acyclic. So you have a hierarchy of modules.
Yeah.
Which means you cannot do recursion. So did you consider cyclicity, allowing cyclicity?
In the quantum algorithms, we usually do not allow acyclic flow, because quantum are usually just one flow from the beginning to end. That's all.
That's logical.
That's logical.
Physical, and you're now trying to compile the physical. And so if I have a module that's reused 100 times, I'm really looping on that module, passing in a state vector on one end, getting it out and passing it back in. So you really are looping.
Yeah.
So you do get recursion.
Probably like this one.
Right. So
sometimes here, sometimes here, sometimes here, they have to use the same modules because not because I mean just repeatedly.
well, so the way I read, you can go back to your further slide. The way I read the approach is you take an algorithm, you figure out the common modules
Yeah.
up to a certain level of abstraction.
Yeah.
So you have the very bottom here, you may do TOEFLs, you may go higher than that. You may say, I have a QFT, I have an adder, I have whatever.
Yeah.
You implement some number of those in the hardware.
Yeah.
Then you have a scheduler that decides, oh, in parallel I can run these, versus these have to go sequential because I only have so many QFTs,
Yeah.
for example. So I can only run this one, and then this one has to wait.
Yeah. Yeah.
And so what you're doing is doing a layout not of the algorithm, but the modules the algorithm needs, and then you're scheduling the algorithm on top of that.
That's true.
Is that correct?
That's correct.
Okay.
So that's actually that is architectural level scheduling. We could. So maybe I can skip some slides. So by using this one, and by using this one, we can make parameter passings. So this is one. This is what you are saying. So this module 1 try to call this module 3, and this module 2 also try to call this module 3. But sometimes they try to access the same modules, but the architectural, high-level scheduler have to control this kind of conflict. So that is the job of the high-level scheduling. And also, like the previous questions, if module 1 try to call this module 3 several times, then the high-level scheduler have to do that. They just need to map. They just need to map the input qubit to somewhere here, and because we already found that scheduling and layout of the module 3, so we don't need to worry about this part. We just pass the input parameters to some place here, predefined place here. Then we just use the same schedules. That means this is the advantage of this kind of approaches. If we have a schedule of the low modules, and if the high-level scheduler can schedule for the mapping of the input, mapping the parameters, then we don't need to worry about the low-level part during the high-level scheduling. Okay.
But a module could be as small as a single gate. For instance, if I have to do a phase estimation with a reset, I need a C0 in one place.
That's correct.
And have to be able to do it. Okay.
That's the job of the second part. I call that is low-level scheduling. This is just for high-level part. I just assume that this is encapsulated modules. But as you mentioned, that we have to decompose again. So this is a very big view, the top view of the architectures. So we can put this bus somewhere here. Oh, by the way, we don't know which way is the best way to locate this bus. But we have an idea like that way. So we can put a bus like that way. And this blue one is modules. And one advantage is this is magic state factory. So this magic state factory can distribute magic state any place in a constant time if there's no conflicts. Okay. So this is I think this is very, this can support very cost-effective way. This is a hardware view. And the next one is low-level view, low-level architecture and low-level scheduling. So we have to decompose these modules. It's the same, very similar way. So maybe the very naive idea is to put one-to-one or a complete way, all combination, all channels for the all combinations. But I think this is stupid. So we have to use some resource efficient way. So we have to put some bus like that one. So and then the key problem is we have to partition this circuit, or we have to partition the group of the qubit into 4 terms. So these shared bus have to be used for all 4 combinations. If this module want to communicate with the other modules, sub-modules, then this bus have to be used, and also this one have to be communicated with the other 2 modules. So this partitioning have to consider the connectivity or sensitivity of the circuits. So these shared bus have to be located on the very sparse or very low connectivity component, low connectivity parts, not the highly connected part. So technically, this part contains this part has very high connectivity compared to these connections. Okay, so we have to partition the input circuit based on these conditions, and then we have to put the bus so that this single bus can support all combination of the communications. Okay.
One other question: the bus is a lot more sophisticated, I would assume, than what people think of as a bus, because it's constantly generating EPR pairs and shipping them everywhere for the teleportation, for the CNOTs.
So,
Same thing.
Yeah.
so also we have a very strong argument about that issues. So at the physical level, we have to do that, like a repetition, generation and distillation and other things. But from after level 0, after physical level, we can assume that we can apply the logical level bus schemes.
But it implies a bandwidth then, because if you
Yeah.
guess wrong and put the wrong pairs
That's
to the
true.
wrong places,
That's true.
you're going to cause a latency
Yeah.
that you wouldn't have had
Yeah.
if you didn't have to do
Yeah,
that.
yeah,
Okay.
that's true. That's the reason why I put like that way. So it depends on the bandwidth. We have to increase, even though this is a vertical one, but sometimes we have to make a very thick buses. But we don't know yet. I mean, which way this is good. So we just up to now we just devised conceptual way. So this is one example. We consider one module like this way. So this is just handwritings, but you can see that there's a location of the bus like these forms. But we also, I think we also have to consider the ADCR optimals. So even though in this case, the granular, the number of buses is very large. So we have to reduce some number of buses based on the ADCR optimal criteria. But we don't know yet. I mean, we don't know yet means we do not have any tools right now. But we are considering that kind of issues. So this is a whole view of the architectural part. So this is top level view. I mean, high level view. So we can map the algorithms into these forms based on the modules and based on the hierarchy. And each component in the architectural part can be decomposed like that way. And also this one can be decomposed like that way. So this one is what is your questions. So we have to build up some physical or level 0 components like a core, router, repeaters. We have to use these elementary tiles to make a bus or communication channels. But luckily, in our project, this is not our job actually. So GTLI people, they do that. They implement this low level, I mean, the level 1 scheduling for implementing level 2, level 1 components. So they input is like a physical level circuit and physical level components, and they generate level 1 component, like level 1 core, router, repeaters. From that, we can build up. Okay. Yeah, I have to say that at the physical level, we have to consider distillation protocol, we have to consider repeater protocol, many things. But this level, we don't need to do that.
Well, there's also the problem of lifetimes.
Yeah.
So sending the pair doesn't mean you have it for more than a certain period of time before you have to send it again, even if you didn't use it.
Yeah. So I didn't show yet. I didn't show this slide, but we have a very important question. The location of the repeaters. Even though we assume that we need these length bus, but we don't know the good location of the repeater. How many and the locations? That question is also one of our questions. And based on that, the analysis is just simple. Okay, because we know that how to do that, how to lay out, how to schedule. The analysis is just to make some programs. So that's for my architecture part. But from now, I want to talk about code convergence. So we can imagine these cases. Computing system A use one code, like a Sting code. Computing system B use another code, like a Sting, like a Bacon show code. Because some regions, they have to communicate. I mean, this is natural in the cloud systems.
What are the codes for
Error correction code.
error code?
Yeah, sorry. Error correction code.
There are different code spaces.
Yeah. So to make a connection between the computers, we have to consider these problems.
Sorry, why would you have two different codes in the first place?
I mean, I don't know. Why?
How can you rule it out?
What if somebody wrote a library using a specific code,
Yeah.
and you're off in another library using a different code, and you want to use their calls? You have to convert between your coded form to their coded form, in the classical sense. On a quantum machine, it's a whole question of when would we actually be to the point where we care about
I guess that's what I mean.
Right. But it's an interesting question. How practical is a different question.
That's correct. So up to now, we have two methods. One is code teleportation method, and another one is a stabilizer sequence method. Code teleportation means if we prepare encoded EPR pair from between the code A, error correction code A, and error correction code B, then we can do just the teleportations. So this is called code teleportation. Sorry?
You can do what?
Teleportation.
Teleportation.
And the stabilizer sequence method means we can find some sequence of stabilizer gate operations from one encoded state to the target state. But in this case, we have to find the sequence. Okay, so actually, Austin Fuller makes some programs, software programs, how to find that. So technically, we have two methods, like teleportation method and the stabilizer sequence method. This work is a little bit related to like a state conversion research work. But this one is just for based on the practical, based on the trivial idea, like teleportations. Maybe we can propose another method, but I don't know. I tried several times, but I cannot find it anywhere. Maybe we can find another ones. So related to this, I'm considering some technical cases, like these cases. This one is Sting code, and this one is Bacon short code cases. How can we make one specific preset circuit for doing the code teleportations? So this slide shows that how to prepare EPR state, encoded EPR state for the code A, in this case Sting code, and for code B, in this case Bacon short code. So I found that this circuit works correctly. So we need to prepare the cat state, and we apply this H gate transverse array, and we apply the CNOT, this part and that part. These all things are transposer. And we just measure some part of the cat state and the other part of the cat state, and then we just check the parities. Based on this parity, we just apply the encoded X gate operations. So this is just like compensations to make an EPR pair between this one and that one. So this is one circuit.
I don't understand how you re-encoded. How did you send one code to another?
No, this is just for preparing the EPR pair for code A and code B. And we can do teleportation by using this EPR pair.
But the pairs are in different code spaces.
Yes. This one is from the code A.
Yeah.
This one is code B. And this one, cat state.
No, I understand the cat state. What I'm trying to understand is code A may have a different number of qubits than code B,
Yeah.
for example.
Yeah.
So how does this teleport from one to the other?
No.
No.
So he's preparing
Just the
an
EPR.
EPR.
No,
pair.
this is just the. I'm sorry. Okay, you may have to see how you're going to use it. So let's stop. Okay, this gives you now a fully entangled between the two, and they have some sort of base they agree on, basically, at this point.
Yeah.
Okay, you're at that point. Fine.
Yeah.
Okay.
And this is one way how to make a fault tolerant scheme for this circuit. So we can prepare this logical process state for the code A and the logical process state for the code B, and we can prepare this cat state fault tolerantly. And this is transposer. So we don't need to worry about that. And then because of this one makes some errors. I mean, some here, there's errors. So we have to apply 3 times. We have to do 3 times for majority votings. So after every job, we have to do quantum error corrections for the error corrections, so that at the end we have to apply the X gates. So this is 1A how to do that. But this is just one case. So now we consider some application of these cases, this idea for reduction of resource overhead for some gates, especially T gates. In our calculation, the T gate on the Bacon-Shor requires a lot of gates, a lot of qubit, because Bacon-Shor T gate basically based on the magic state dissolution protocols. So we do some preliminary work. If we can change, or if we can convert Bacon-Shor encoded state into Reed-Muller encoded state, and if we apply the Reed-Muller encoded T gate, and then we can recover again into the Bacon-Shor encoded state. But the issue is the T gate on the Reed-Muller code is transposer. Okay, so some T gate can be replaced by the transposer T gate on the different code. Okay, so thin code T gate and the Bacon-Shor T gate is non-transposer, but Reed-Muller code T gate is transposer. So if the cost for the code conversion is small, then we can replace Bacon-Shor T gate into Reed-Muller T gate operations. Okay, that's the main idea. So this is our preliminary data, but this is not the correct one. I mean, this is not the precise one. So our rough calculations show that for the sting code cases, if we implement a T gate on the sting code, we need this amount of resources. But if we apply the code conversion, and if we replace the sting T into Reed-Muller T gate, then we need this amount of resources. In this case, this is not good. But in the Bacon-Shor code, as I told you, Bacon-Shor code requires a lot of dissolution overhead, so that we can replace this amount of resource overhead into small one. Okay? So if we use a Reed-Muller T gate, then we just need this amount of resource overhead. This is the original or conventional case resource overhead. Even if we assume that the fidelity of the magic state is very high, like 1, but even in that case, the resource overhead is very big. But if we can use the Reed-Muller T gate, we can reduce this resource overhead into these values. But we can go further, because thin code T gate is much more simpler. So we can replace again into thin T gates. So conclusion of this slide is, if the cost for code conversion from one code to another one is smaller than the some gate like a T gate, then we can replace it. We can replace the complex T gates into.
You haven't shown the code conversion.
Yep.
Okay.
And where's the threshold? I mean, on these codes, isn't the threshold for these codes somewhere, 10 to the minus 5 on the top one? Some of these error rate numbers don't make sense because you're above threshold, you can't correct.
Oh yeah. So
the only numbers that would make sense are the ones that are below, that are below threshold.
Yeah, probably this.
Significantly,
This boundary.
below.
Yeah.
And then it looks like even using these code conversion things, the top one is still better, right?
Yeah.
If you look at the single code model, the resources are always smaller at the below threshold.
The 932 that you see up on top is never beat by anybody else.
I mean, you'd never use the Bacon-Shor code in that scenario.
Right. Because even down at the bottom, it's 2,800, 2,600 gates.
Yeah. Yeah. So technically and practically, we have to consider these areas,
Mm-hmm.
Right.
these boundaries and these boundaries. We don't need to worry about this part.
Right.
And there's no benefit
Yeah.
in that case.
And then it seems like it's too expensive.
Yeah.
Right. And that's before the cost of the code conversion.
Yeah.
Oh.
So this one, this error rate is 0. These are ideal cases.
Mhm.
And this one is fidelity is 1. So this is ideal case
Mhm.
costs. Even in that case, the code converter can show that the advantages.
So I'm curious, do you have the same numbers for the single code model for Multiplier code?
Yeah.
Do you know what they look like? So it looks like 932 is the best that you have here for the Steam code. Do you know what the same number would be for read Muller code? Right, because I mean you can do T transversely in read Muller, and you can do basically so you can basically do universal computation transversely
No,
with the read Muller.
no. Rhythm code does not allow gate H as a transposer.
Well, if you're careful, you actually can
Yeah.
do it.
So I just combine the advantage of the coders. So this Steam code and Bacon code has advantage on the H gate and Clifford group gates as a transposer. But the Rhythm code shows the advantage on the T gate only. The other gate, like H gate, does not allow transposer. So I just combine the advantage of the both of
We can talk
cases.
about that later, but yeah, it would be interesting to see the numbers just for read Muller.
And also, I think this is a more practical reasons. We have to consider code conversion on the repeater part. Repeater usually used for communication part, and the repeater have to consider error correction as well. So repeater have to consider code conversions in near future. So that's all my current consideration on the system part, and also I also consider some issues on the application part. So just one extension of my previous work. I want to know that is there any quantum algorithms for the resiliency and nonlinearity checking of the Boolean functions? These two primitives is very important on the security part, because Boolean function is used for symmetric key systems. So they want to know that they want to check this resiliency and nonlinearity as quickly as possible. But up to now, there's no classically efficient way to check this resiliency and nonlinearity. So now idea is whether the quantum computer can help them to check these resiliency and nonlinearities efficiently. But I am working with another fellow, but we still found some just not good. I mean, it's not good. Not good means it's not like a super polynomial speedup. It's just like a sub polynomial speedup. It's possible. And also, I want to know that what's the query and circuit complexity for these problems. That means I want to know that what's the limitation of the quantum computation on that problems. And also, we can expand this problem into post-quantum cryptography domains. And the second one is machine learning. So because Boolean function can be used for cryptography and also for machine learning. So I'm considering to use this algorithm for machine learning, but I'm just starting. I don't have any ideas. So ultimately, we can make a quantum being much more useful for quantum being, such algorithms. So that's all. So currently, I'm working on these issues. In the architectural layer, I'm refining the low-level and high-level architecture and their scheduling and layout algorithms and the analysis method. And the arithmetic part, we are trying to find some best way to put the error correction and the locations. And the code conversion case, we try to check the fault tolerance level of our proposed circuit, and also this is used for the architecture part, and the cryptanalysis and machine learning. So this one shows that my currently research target. Architectural level resource reduction is my main goal by using the arithmetic and code level optimizations, and also compiler level resource optimizations. Because Alex is here, so I'm considering to use high level optimization method into architectural part. So like a vertical optimizations. Yeah. That's it. Thanks so much.
Questions for Yansu?
So I have a question. So you mentioned, so you have some concatenated code scheme, basically what you normally do is error correction followed by the encoded gate followed by error correction.
Yeah.
Repeat. And you mentioned that you could optimize potentially by eliminating some error correction steps in
That's right.
strategic places.
That's
I mean, you have a strategy for how you might go about figuring out how to do that?
One of approach is to consider the graph theory as well. So in the graph theory, you can find that the weakest or the congestion node. Congestion node means this node affect all other graph edges and nodes. So this is very important node.
So error at that node
Yeah.
spread.
Yeah. So maybe we can use that approach for this case.
Graph centrality algorithms are extremely expensive. So depending on the size of the unit you want to look at, classical processing is very hard to figure that out.
Yeah.
And in the general case, you can't solve it. You have to do it for each graph that you generate.
Maybe we can use that, even though that case is because we just need to optimize some component. So we just need one.
For the standard block, yeah, you're going to do some specific adder,
Yeah.
multiplier, QFT.
Yeah.
Yes, that's the scale.
At the high level, maybe we don't know
No.
that.
Do you have any intuition for how much you might save by doing such a thing? What kind of multiplicative factor you would get?
Oh.
I mean, I suppose that would depend on what module you're trying to optimize, right?
Yeah. So recently, there's one paper already shown in the literature. They consider their title is like how we have to error corrections every time, such kind of things.
Okay.
That's the title. So they also consider these
Who were
problems.
the authors on that?
Weinstein.
Yeah, but
Oh, okay.
What they find there is they just look at a sequence actually because of decomposition. They look at HTH or HT or our favorite sequences. And they just basically show analytically that the maximum you can go typically is 2 or 3.
Depends on the sequence, obviously.
So that's for single.
Because that's the lowest level sequence.
Right.
They just consider that sequence.
So okay, so this is
And
just
they
single
consider
logical
steam,
qubit.
713 code.
Yeah.
And they just say that, okay, if I don't error correct after the H, and
Yeah.
so they look at TH, HT, different permutations of this, and say if I don't error correct after the H and I just error correct after HT, what happens to my failure rate? And they give a table of it. Essentially, they say, I mean, to me, it means maybe you save a factor of 2.
I see.
Is-
Okay,
was my
and so they're not, and so that's
conclusion
only
from
for
this
single logical qubit. Okay,
They
so it's even
only
worse
looked
for
at
2
single
qubits, I
qubit.
would imagine.
And the other work that I know of that looked at that was out of Kubi's group.
Okay.
And they look at it in a slightly different fashion. They just consider that the error correction tiling, kind of how often they apply error correction in the short code. They try to optimize that, and I think the factor was much larger than just a factor of 2. And they actually simulate it.
Okay.
I mean, parts of the task, some of the modules, and find, I think it was higher, like, I don't want to say exactly, it was like either.
It wasn't that,
Okay, but
it wasn't that
1,000.
big though. It
But
still
we're,
Was that
we're talking
1,000 or
maybe
less?
factor
I
2,
don't
factor
remember the
4,
exact number.
rather than say like a factor of, I don't know, 100 or something.
No, this was an order of magnitude plus.
Oh, really?
If I
Really?
remember correctly in the Kubi paper. But they make a lot of assumptions on the architecture.
Yeah.
I
Like you're
mean,
not going
it's
to gauge the same error in the same place, within
Yeah,
a certain
there's-
delta and on and on and on.
I
Yeah.
can point you to.
That's right. I remember that now. Yeah, if all the world is working for you while your faults are going on, you
Yeah.
have one
It all
order of
depends on the
magnitude.
Yeah,
assumptions.
All right, last question on that related topic. I mean, do you think that kind of same thing could be applied to topological codes? So for the surface code in particular.
honestly speaking, because surface code is not our part in our project, we did not consider. But probably, I think in the surface code, we can make a graph based on the rotation, based on the braiding operations. So maybe we can make a graph structures same way. So the distance, in this case, the distance, because I think we can put the defect as a node in the graph.
Defect.
On the surface code. And the distance for example, CNA operations, we can make a long distance edges. So maybe we can consider those kind of information as like weight of the edges. So in this case, we do not consider weight of the edges. I mean, what kind of information we have to put as a weight? But in that case, maybe we can put some distance as a distance, the distance as a weight for the graph. Then maybe we can use the same algorithms. I mean, the key idea.
Results in some
Yeah,
way, right?
but I think part of the problem here is that we're only in these experiments or simulations. People are just looking at depolarizing noise. And that paper from Austin and John this morning
Martinez, yeah.
basically shows that these leakage errors are a huge problem in the superconducting qubits. And the way they propose, I mean, I didn't read the whole paper yet, but I did read the abstraction and conclusion. And basically, it seems that you're gonna have to measure these qubit. They actually want to move to maybe a full measurement cluster state scheme instead, because
given the earlier assumptions before that paper,
right?
I mean, Austin did a bunch of work in terms of given the length, between your defects, right? How long you could wait before fixing things before your matching went bad on you, right? I mean, there was a time, but there was a time delay depending on the depth that you could wait.
But I think he's assuming error correction at every.
Yeah, but you're not doing it on every time step. That's the point.
No, you don't decode every time step. You error correct every time step.
Yeah.
Oh, even without the
Different
decoding.
question.
Oh, no, that doesn't help. Okay.
But this new paper says that basically the leakage is the
Is so bad. Is
the
the
problem
big
you actually
thing.
need to
Yeah.
maintain.
Well, people are
this
starting to
other-
do non-unitary noise. They're realizing, oh my God, that's what's going to kill us more than anything else. Yeah.
So I don't know.
Okay, so sorry for the extended question.
No, that's fine. Do you have questions?
I guess I have one more question. On the adder circuit work, when you did the square root of n, you assume there's no change in the width for that embedding? Because if you add more qubits, you can do it in constant time. So, constant depth. So you must make an assumption on that.
Well, he had the same number of qubits as the bits he was adding.
Yeah,
right?
that's what I was asking.
Right, he
just
never
to
went further.
verify that
Right.
when you do the proof, you actually add no additional qubits.
Yes, that adder is not the optimal one, right?
Nah, it's a long way back.
Yeah.
Yeah, it's okay.
So that's just like try to show that the conceptual way how to change the previous adders by using the Boss schemes. The Boss scheme means we can reduce the delay from root n to 1. Okay, but as you know, the one column requires a carry flow, so this requires root n times. So this is not the optimal one. But I just want to show that this is just one way how to put the Boss on the adder circuit. It's not for showing the optimal one. But maybe we can use, I mean, if you have an architectural level scheduler and layout tools, then we just need to use these tools for adder circuit. Adder circuit can be the input for this scheduler. Then we can look at that, the layout of the adders.
Are there any other questions? Let's thank Yansu again.
Thanks so much.